and he actually is going to defend this Friday. So he's one of the few students that, almost reached the line. And today he's going to give us a preview, and he's going to talk about the categories of the digital techniques for digital forensics for investigation.
Thank you. That's all right. Thank you. So the official title of this is Categories of Digital Forensic Investigation Techniques. And as Christina said, this is kind of a subset of my defense. This has got less theory, kind of skims over some of the formal model details, since no one really wants to see that kind of stuff unless they have to in most cases. So if you really want to see more of that kind of stuff, you can go Friday morning at 10. Otherwise, I guess not. So the overview of this is basically, there'll be a motivation for what this topic is, basically a description of the model we're using, the analysis categories, which is the main topic, and then the evaluation of the existing tools to compare how they, what they support of these category analysis categories. So first of all, before we get into this, who here has actually taken the forensics courses from the course School of Technology or Mark and a few people? Okay. So the first thing we're going to discuss actually is kind of the basics of what are we actually talking about, digital forensics or digital investigation or computer forensics, these other terms that are used. And so the common definition you'll see a lot in the various books. Did that go up? It's going. All right, there we go. So the common definition you'll see a lot of times in books and in other literature is basically it's a process that involves the preservation, identification, extraction, documentation, and interpretation of computer data. And this is kind of a classic definition of the field. And we basically see here that there's some kind of process involved with this, where we actually preserve the state of a computer that we're investigating, we identify certain pieces of evidence, we extract them out, we document them, we interpret them. And there's some kind of implied process with this and some kind of taxonomy of what's involved with this. The goal of this work is basically a more formal discussion and analysis of the process. And this is kind of limiting because it shows some kind of taxonomy that we can't really show as complete. And there aren't phases that are missing or that shouldn't be there if they don't need to be there. So the definition that we're actually using is a little more formal. No, it goes too far. Okay. So the process we're using here is it's a process that formulates and tests hypotheses to answer questions about digital events or the state of digital data, which is basically kind of this more general abstract process here that we're just kind of talking about events and states. And we're not really saying how we're going to do this or in various ways. But the main point here is that we're trying to answer some kind of specific questions. So for example, does this file exist on this computer? Or we found evidence of some kind of malicious activity. What events occurred prior to that to make this happen? Or did this user download, child pornography or some other unauthorized files at work? So there's various questions that are asked to start an investigation, and we want to say formulate hypotheses in terms of did it occur or did it not occur? And it's basically been an ongoing process, starting with the 1980s, with probably before that, with computers being investigated, and they would take the hard drive out, boot up DOS, use some interrupt handlers to prevent from writing to it, and basically just kind of browse through the computer and hard disks. And now we have much more specialized tools where you make a copy of the system, you put it in your analysis tool, and it recovers files and gives you timelines and all these other fancy things. But there's a kind of underlying problem with this, that there's no real theory to it. It's just kind of a general process. It produces good results in many cases for trials and for other cases, but there's no real underlying theory to it, like you will find in physical forensics, like that involve biology and chemistry. And so as an example, there it goes this time. There we go. So in the physical world, there's this concept of transfer and divisibility. And this is basically a core concept that underlies a lot of physical world forensics. And it's based on the following theory, that basically physical matter divides. I can take a pen or this water, we can break a pen apart or a pencil apart, I can tear paper, and matter easily divides. No problem, everyone kind of accepts that. And in some cases, there are some characteristics between these two things that break apart that allow you to link them together again. So, another example is blood, that if I lose some blood here or some other tissue, There could be DNA that links that tissue back to me. There's that unique characteristics that link two things back together again. Same with bullets, that when you shoot a bullet out of a gun, there's some transfer between the gun and the bullet. You can link it back together again. And so this is a core underlying theory that you'll see in any episode of CSI. Involves this basic core theory of transfer divisibility. But this doesn't really exist in the digital world, or it's not clear if it exists in the digital world at least. And so the question is, well, what kind of techniques and concepts and theory apply in the digital world? And so there are many examples. The first thing we looked at was this notion of process models. And these are used a lot of times for training education purposes of basically, these are the phases of investigation that you need to go through and apply and use. And there are lots of these. We proposed some, and there have been many others out there. So here's a basic example. This is from the NIJ, which is the National Institute of Justice. And this is their process model they have. The first phase is preparation. We prepare tools and people and the setup for the actual investigation. We collect data. We copy a system, or we do some other data collection. We do examination. And the terminology they use for this is make the electronic evidence visible and document the contents of the system. And we do data reduction to identify the evidence. So I'll get into my pet peeve here in a second with these two terms. And there's analysis, which is you analyze the evidence identified in the previous phase to determine what is significant and what has probative value, which basically means what evidence can we use in a court of law for this case. Then there's the reporting phase. Now, the one problem with this kind of definition is there's this examination analysis. And if you look at the definitions of these in a dictionary, they refer to each other. That basically, examination is a form of analysis is a form of examination. So there's this kind of weird, what are the difference between these two phases? Is there really any difference before these? If we're trying to find the underlying theory, is there at the core any difference between these two? And if you look at these, the first one is basically, they say it's a form of data reduction. That we're trying to extract out this huge, hard disk, certain pieces of evidence that are relevant and that we think are interesting. But on the other hand, the analysis phase is also a form of data reduction. We're trying to find out of this smaller corpus which ones are actually relevant to the case at hand. And so it's kind of tough to determine whether there's actually different technical requirements in theory of these two. The reason there is two differences, by the way, is that a lot of law enforcement agencies are organized this way, where they have technical people and non-technical people. And the examination people are technical people who, so for example, a child pornography case, they take out all the JPEG pictures, all the images from the computer. And so they do this full extraction of all pictures, which is basically the data reduction they're talking about. And then a less technical person will go through each picture and say which one is child pornography and which one's not child pornography. In that case, there's a clear separation between the examination and analysis. But if you're doing an intrusion case where you find a rootkit here or some other log evidence here, there's not a clear separation of these two roles. So this is a model that works very well in some labs and circumstances, but it's not general enough to apply to the general investigation process. And if you go through the other dozen or so process models that exist out there, they all have a similar kind of problem with what we're trying to identify as common categories of techniques, that they are either specific to a certain area of focus, or they're kind of arbitrarily defined, or they just have one phase of analysis that doesn't really give much insight. So the basic goal here is now is to define a whole new model, so that the process models aren't going to help us. We need to kind of start from scratch with this. And so basically, this model and concept is based on this notion of a history. And the proposal is that every object has a history. So this bottle of water in the physical world has a history. And the physical world is based on what stimulates its senses. And of course, there's no senses for this bottle because it's not alive. But you can imagine the concept of touch and sight, of a camera can see things essentially, and light touches film to record various things. And so there's this notion of a history that we have with all these objects. And basically there's multiple levels. So in the physical world, there's a molecular or a quantum and a physical, a higher level object level history. And investigation occurs in this room, and they're trying to investigate, what Brian Carrier did. They're going to analyze the objects to find out, when there was contact between, Brian Carrier and this object to find out, if I'm in the history of these objects. And the basic concept is that there's the history is never fully known. But the goal of the investigation is to determine that history as much as possible and try and make inferences about that history. So this is kind of clear and kind of, we can see this for the physical world where, witnesses are used to see what they saw about an incident, or, objects are analyzed to find out who touched them or what they've been in contact with. So the question is, what is the history of a computer? Because they don't really have senses as we do. So the basic argument in this work is that the history of a computer is basically the sequence of states and events that have occurred in this system. And this is kind of, again, a theoretical notion, and this doesn't always record it each time, but it's this notion that the sequence of events that occur in the computer are its history, and it's what we want to determine with the investigation. And as we'll see later, these occur at both primitive and abstract levels. Primitive meaning CPU registers, CPU instructions, hard disk sectors, the core low-level events and states that occur in a system. And there's abstract events and states as well, like files, system calls, or user-level events of clicking on buttons and various things that occur at multiple levels. And basically, digital investigation is basically a process where we make inferences about the previous states and about the previous events that occurred on the system, maybe given only one state of the system. We try and figure out this other history of it. So now we kind of get into some of the formalities of this. So the basic concept of this whole model is based on a finite state machine definition. And so for those of you who have forgotten or want to forget about all these various things, the three parts we're concerned about for the finite state machine definition is we have a set of states, which we're defining as Q. And this set basically contains all the possible states the system can undertake. And basically, if any bit in the system changes, we're in a new state of the system. We have a set of possible events, which are in our alphabet. And these basically denote which events are possible in the system, which are supported by the system. And there's a state change function which maps a given state and a given function in a given event to the resulting state from that event. Now, the important thing here to note before everyone says, this is bull, that we're not saying we're going to represent the computer by a finite state machine during investigation, because that's quite clearly impossible, or not impossible, but pretty much impossible to do with a modern computer that has millions of instructions and gigabytes of RAM and gigabytes of terabytes of storage. It's just not possible to actually represent that as a useful finite state machine. But we're using this as a general theoretical model so that we're not limited to any certain architecture or system. So as I said before, there's histories at the primitive and the abstract level. The first thing we're going to address is the primitive state history. And it's basically, with this, we're going to address again. That's going to jump ahead like 5 slides at me. Yeah, see? All right, so the history itself maps a time to a state in our set Q, which is our finite state machine definition. So we have this counter, this notion of time. We won't get into the details of this right now, but there's this notion of a time that basically the history maps a time to whatever state existed at that time. So I get in trouble now. All right, forget all these animation things. So we have this set of one of the problems with this, though, is that in a real computer, this set Q, which contains the possible states the computer can have, can be different at 2 different times. Anyone know why? So if you add a USB token or a floppy disk or a CD-ROM or any other storage device in the system, we now have an entirely new set of possible states in the system. So if we want to account for the history model to account for the entire history and possible states of the system, we actually need to account for which various storage devices were connected at each time in the system. So our finite state machine model actually has to account for this, that the set Q, which has our possible states, is a dynamic set that's going to change, or could possibly change for each time in our history. So basically the model needs to map each time. The model needs to map each time basically to the set of devices that were connected that time And we also need to know what possible states for each device. We actually need to basically combine all these various things of knowing the possible states for the device, which devices were connected, before we can define what our possible states of the actual system are. And we basically determine the possible states by how many addresses there are on the hard disk or other storage device, what the domain of each address is, what are its possible values, and we merge these and combine these and work our way up to define our set Q, which we can then map to for the state at that given time. And examples of this state include registers in the CPU, hard disk sectors, memory bytes, all the low-level things that we never really care about, but are the underlying storage devices of the system. So that's the primitive state history. We also need a primitive event history. All right, I'm just going to go ahead here until we get them all. All right, I don't know how to understand this, but so basically our primitive event history is mapping a time itself, again, a time value, to an event in our alphabet that occurred during that time frame. And again, in the same case, the set of possible events that can occur at 2 times are different because we can have 2 different sets of event devices that are connected. So our model needs to map each time to the set of devices that were connected, and we also need to know which events were possible with each device. So, for example, low-level primitive events are CPUs, memory management units, other low-level processors on a system that can change the actual state of the system at any time. So here's a basic example of what we're referring to here. That this column here is basically we're representing as a storage device or a set of storage locations. So these are registers, R1 through R7, for example. So at time t, the value of all of these represents the history of the state at that time. We have some event here that occurs at time t that maps, that writes a new value to this register R3. And so the state at time t plus delta t is now whatever values are in all these registers at this time. So this is the second history marking. And this goes on and on and on. This entire process, we have events followed by new states, followed by new states and events. So basically, in summary, for the primitive level, hold on a second. We define the capabilities of each storage device and the event device as our first basic thing. Then we define which devices were connected each time. And then we determine actually which actual state or event occurred. But there's a problem with this underlying process is that who really cares about primitive states and events? When was the last time you heard investigation started because asking whether the load instruction or the add instruction was executed, or if register 5, had the value 800 in it. The real concern is about files and user events. Did the user download this file, or is there contraband, pornography on this computer, or various higher level events beyond CPU instructions, registers, hard disk sectors. So this is kind of the primitive history is what actually occurs, but it alone is not going to answer our questions. If, this investigation is trying to answer certain questions. This isn't going to help us directly answer those questions yet. So we have to account for, excuse me, the abstract systems. So to define the abstract system, we actually have to define new finite state machines for various levels of abstraction. Okay, the details we're going to kind of skim over for this discussion. If you want them, they'll be Friday morning. But there's 2 notions we're talking about here. One is the abstract storage locations. These are virtual entities that can be used to store data. So a file is the most common example that everyone's used to. A file doesn't really exist in a physical or any kind of form. It's really just a representation that's created by transforming sectors in a disk to make it look like a file, but it doesn't really exist anywhere. And there's many other examples. Any data structure we use in a programming language is essentially an abstraction. You're taking bytes in memory and you're grouping them into a 4-byte integer or an 8-byte integer or a floating point or some other larger abstract storage location that's being mapped to and transformed by some lower level primitive storage location. We also have abstract events, which are basically one high level abstract event which causes multiple lower level events to occur. So common example is I hit my button on the screen to change slides, and there should be events occurring. Below that, it's one event for me, but it's actually hundreds or thousands of lower level, primitive implementation level events that are occurring. But from my perspective and standpoint, it's one event. And so basically we can define a history for abstract states and events as well. This exists. Depending on what level of detail you want to get into, there are multiple levels of abstract events. So there's a user level events, there's implementation level events, which are programming language events that occurred, as well as the primitive ones. And depending on what software engineering model you used, there could be other layers of abstraction in a program itself. So as an example, before we had the representation of the single event at each time, now we have this notion of D1 and D2 as being these abstract data locations. E1 is an abstract event which writes to this abstract location D1 at a given time. But underlying all of these locations are these lower level storage locations and lower level events that are doing the actual reading and writing in this whole process. And so now we can actually start mapping the abstract state history, event history. And so the abstract state history basically maps a time, again, to some given state. In this time we have a subset, subscript X in here, which for now we'll just kind of assume this is the abstract states that can occur. Now to define this is actually pretty complicated, because the possible system states, the possible abstract system states, are based on the abstraction types that exist at that given time. Because an abstraction type exists only because a program creates it. So if the program doesn't exist to make that file, then the file doesn't really exist. So, a common example of this, this situation is someone emails you a WordPerfect file or some other file that you really don't have the program to interpret that data anymore. For all intents and purposes, the other storage locations and data structures and abstractions in the WordPerfect file don't exist to you because you don't have the program to properly interpret it. It's just another file to you. You can't actually store the author's name or change the paragraph settings or change the paragraph content because you don't understand that actual storage location. So to determine the possible states of the system at a given time, we have to know all the various programs and abstraction types that are supported at that given time. And to do that, we need to basically determine the possible states each time and then which programs existed to build up our set Q sub X. And this is actually a very hard problem in terms of, this basically requires analyzing every program on the system, which we don't do in practice because it's way too time intensive and very complicated and error prone. So in practice, this is one of these cases where a lot of assumptions are actually made from the actual theory of this. Similarly, we have the abstract event history, which maps a time to the abstract event that was occurring at that time frame. And again, we have similar problems, where the abstract events only occur because of what programs exist. So we have to analyze the programs to find out what events could occur and analyze them, which again involves some form of static or dynamic analysis. And again, it's a relatively hard problem. And in general, many assumptions are made about this process in practice about what events could have occurred or did occur. So in summary of this process, the abstract history, the process is basically to define the capabilities of each program on a system and then determine which state existed or which actually event occurred. All right. What I get for trying to add some sliding in there. So if we readdress our digital investigation definition, the process is we basically start with one or more known states, and then we try to determine the rest. So if we look at our primitive state history, for example, the typical process is you get a hard disk from the suspect, you make a copy of it, and you import it in your tool. Basically what we're doing is we're starting off with one known state, one known primitive state of the system, and then we try to determine what the abstract states are, what the previous primitive states were. We try and fill in all these parts of the history that we don't know. And it's generally inferred histories because we only have one state in time, and we make inferences about what occurred, about what files occurred in the system, about what deleted files were, what files that are now deleted, what they were before. We try and make inferences about previous states in the system. But there's one problem with this concept, and the problem is that what are known states when it comes to a computer, and how do we actually know anything about anything? This is kind of one of these philosophical discussions, which we're not going to quite get into about how do we know what we know and all these various things. But in general, we're taking the assumption with this thing that we know what we can observe. And I know that I'm wearing a green shirt because I can observe that this color is green. And in the past, I've been correct with the assumption that when I thought it's been green, it's actually been green. Now, if I'm colorblind, we get into some problems here. But it's an assumption that if someone's telling me I'm wearing a pink shirt, I'm going to believe my observation over someone else's because it's actually a direct observation that I'm observing directly. Whereas an indirect observation is something someone else tells me. So someone can tell me what someone else is wearing. I may or may not believe it depending on if I trust that person or if I have contradicting evidence. And the main point of this basically is that any indirect observation is a hypothesis. That it's not a fact. We can usually assume that what we directly observe is fact, but that indirect observations are hypotheses that we may or may not test to certain degrees depending on how much we trust the source of this information. The problem with this, going back to digital investigations and digital forensics, is that everything about digital states is indirect. There is no way that I can directly observe the state of a computer without using tools and hardware. I can open up a disk and look at the platters, but I can't actually recognize the actual value in those platters until I use hardware or software to help me in this process. And therefore, everything's an indirect observation and a hypothesis. Which brings us back to the original definition I gave of that the investigation process formulates hypotheses about states and events because we actually never know anything for a fact. So with this model, and we can actually, in the thesis and all these things, we can prove that this model represents all of the states and events that occurred in the system at the primitive abstract level. So we have some kind of proof of completeness of this. We get into, all right, now how do we actually apply this model to actual usage? And this gets into the actual main topic of this talk, which is the analysis categories. And based on the history model variables, which we kind of glossed over in this discussion, we can define different categories of analysis techniques. And they're basically broken down into 8 categories. As we'll see later, they're kind of arbitrary. But the point is we can show completeness in that each category defines certain variables. You can organize them into 4 if you want to, 1 category, 12 categories. It doesn't matter as long as they define the specific variables in the actual history model. And then each category has 1 or more classes that can be used to define these variables. And we define some of them here based on what's in practice, just the basic design of the model. And future ones could be developed in the future, which is why there's no completeness proof for these, because new techniques could be developed in the future to define these various variables. So here's kind of an overview of how the 8 are organized that we'll go into in a second. The first one on top is the history duration, which basically says how long has the model been around. I'm sorry, the system's been around. We get into the capability storage of the system, the actual events, and the abstract capabilities and abstract events and states. This is my lesson to remove all these animations for the defense on Friday. This is lesson number 1. So the history duration category is the first one we'll address. And this is actually one of the most basic and simple ones, and one that's actually not really done formally But there's a set t. We had all of these functions that were mapping a time to a state, or a time to an event, or a time to the devices that were connected. So we had this notion of a set t that basically defines what times does this computer exist and have a history. This category basically defines what times they have a history. Well, if we have the computer at the current time, we basically know it exists now. So the real problem is basically to determine when the history of this computer started. That's really what we care about. And actually, even more practically, all we really care about is did the computer exist during the times being investigated? You know, if the computer was made last week and the crime was 2 years ago, it's probably not going to have, evidence from events and states 2 years ago because it didn't exist. So the basic examples for determining these types of things are looking at the manufacturer date of the computer, looking at the OS installation date to find out if it existed at that time, looking at the earliest modified access or change times on a system to see if we can get a reference for when the system was created or used. All these are kind of vague and fuzzy and not really accurate in that we can completely wipe a hard drive, lose all notion of time, and then our earliest time is really 5 years after it was first used. So all of these things, there's no real concrete way to identify the exact date the system's been used, but this is kind of the general goal of these techniques. Second category we're working with is the primitive storage capabilities. So the first category is basically what times this exists. Now we need to define basically our set Q and our finite state machine definition, which is the set of possible states at each time. So all we're going to do with this is basically define which storage devices we have and what their possible states are at each time and when they're connected. So to define the capabilities of each device, we can basically do this with some kind of hard disk spec. If we have the model number on the disk itself, we can find out that it's got this many sectors, this sector is this size. We can easily figure out what the actual capabilities of it are. There's queries we can run on it to have it return how big it is and what its sizes are. We won't get into that now, but that it's possible for devices to lie to you, basically, if they've been modified by the person that's attacked them. So the reliability of all these are in question in terms of what you can trust and what you can't trust, since, again, these are all indirect observations. But these are all approaches that can be used to actually define these various things. To determine which ones are connected to the system at what time, though, we have to rely on various log files that say this hard disk was plugged in at this time, which usually don't exist, quite honestly. I mean, some Unix systems may have a log that says this model number was on their boot up time, but not all systems have that same amount of logging. If you put a USB drive in, you may not have a log record of it being plugged in or not. So a lot of times this is kind of a fuzzy process of trying to figure out when each device was actually connected to the system. And again, you could use MAC times to determine when activity occurred on the disk or the storage location. But again, it's not really a strong, definite reference or resource to determining when they're all connected. The third category, the previous category basically defined the storage capabilities. Now we can define the actual event capabilities of the system. So again, we actually examine the event devices, find out what events they can cause, what their state change functions are, and then try and determine which ones are connected at each time. And the way we do this is basically by specs of the processor, querying the processor to see if it returns the list of commands, and then logs that, to find out when they're connected. We may use logs again to find out when they're connected. In practice, this is basically never done, pretty much because primitive level events are, again, as I said, pretty much useless for investigation to find out when the add command was used. So there's really no need to worry about enumerating all the primitive level events or identifying, which their actual state change functions and such things. But this is, again, in the formal categories of things, this could be done in the future if this is deemed to be a necessary part of the investigation. But even more so, Then with the primitive storage stuff category, there's really no logs at all that record what event devices exist, the CPU ID or any of those kind of devices. So even if that was required, there's very little history about when those were connected to the system each time. I don't get this at all. Okay, so after we've defined the time in the system, we define the capabilities of the system, or what we think are the capabilities of the system at each time. We can then start to define what the actual states and events were. And this is basically, we define what we infer to be the actual states that occurred at a given time and what events occurred. So examples of doing this basically is from directly observed states. So I can directly observe the state of the computer monitor, if you will, or some kind of driver in this because I can see the actual screen on there. So I can define the state of the controller card of this video monitor because I can directly observe it. I can also, through indirect observations, also define other states in the process of going through all of these various things. Can't see it on my own screen here. So other ways of going about doing this are event reconstruction and construction. So if we look at this next slide here, this kind of shows the directions we're talking about here. So we have various ways that actually are addressed in this. We can define a specific state at a given time. Then with reconstruction, this middle one here, we basically start with a known state, a given state, and we consider what the previous event was, and therefore what the previous state was. And with this, we can start with our known state and basically work backwards and go through and try and figure out the history of the system. Conversely, we can do a construction method, basically start with one state, make a hypothesis about what the following event and state were, and move on from there. It's kind of out of the scope of this, but the reconstruction is the much more common method of doing this. But again, at the primitive levels, this still isn't really a common technique. But this is the basic concepts of how we would go about defining the various primitive states and events if we needed to. So at the abstract level, we have four more categories that we're addressing here. This one is impossible, so it's not really much point discussing it, but here's the main concept. So the main concept is in the formal model, in the discussion, we define what layers of abstraction exist on the system. Basically, these layers are based on, as I said before, how the program was actually developed and constructed and programmed. Whether there was, how many layers of abstraction there were in the development process, just kind of based on how big the program is. So this category would define the set L in the model, which represents all the various levels of abstraction. To define this would basically require the investigator or someone to interview or somehow determine all of the program development processes that were involved with developing all programs on the system to find out what layers of abstraction actually exist. It's not going to happen, quite honestly. This is over the entire life of the program. So the program may have started off with one software development model and over the years changed to different ones. All those abstraction layers will still exist in some form. So this is kind of a useless process. But in the formal model, this actually exists. And in many cases, the assumption is basically made that we only care about user-level events, that we only care typically about what the user actually did, what commands they typed in, what buttons they pressed. We don't care about how many layers of abstraction there were between me clicking the save button on a program to it actually saving the file. That we'll kind of ignore those details for most cases. So this is a category, but it's not really done much in practice at all. So the next step here is we have three more, which are basically based on the same concept as the primitive levels, where we're going to say define the capabilities and then define the specific ones that occurred or existed. So the next one, number 6 here, is basically defining the abstract storage capabilities. So as we said before, these are based on what programs existed at each time. So to do this, we have to identify which programs existed each time and basically reconstruct the state of the system at each time, determine which storage types exist in those programs, and then determine the possible states of those abstraction types. So, I mean, just the scale of this, just as a reference, consider that all of the possible states of files is enormous. And you consider that there's, 4 gigabytes or 2 terabyte maximum file size in your file system. All the possible states of those files is enormous. And the possible states of the system is basically all the possible file names and file combinations and files. So, I mean, the size of these sets is enormous. But again, this is kind of the beauty of theory versus actual practicality. And so basically, this is how we go about defining the actual possible states of the system. And to do this, we basically need to reverse engineer stored data. So if we have a Microsoft Word document or some other, storage format, reverse engineer it to figure out how the data has been transformed and laid out and organized on the actual the file. There could be a specification, for the file format we can use to define the different storage types. Or we could use some kind of dynamic and static analysis of the program to find out which ones are being used, or how the abstractions are being used. So in a similar context now, we have to define the abstract event capabilities. Again, identify which programs exist, what events they can cause. They basically map this in terms of what can actually occur in the system at each time based on what existed. And again, this is a process of using specifications if we have them, which we usually don't, and then some form of static or dynamic analysis of the programs to find out what the possible events were. And again, as I said before, in most cases we care only about user level events. So this could just be as simple as running the program and playing around with it to find out what the possible user level events are and what the effects of those events are on the system. And the final category of this is basically then, given these capabilities, given we know what states and events can occur and exist, to actually define which ones did exist and occur. And so basically this is making inferences about the abstract events and states. And there's many techniques of doing this. The 4 listed here are basically event and state abstraction, materialization, and then the usual reconstruction and construction. We have a diagram here, which is a little more complex than before. So basically reconstruction down at the bottom here, as we saw before, we have some known state. We want to reconstruct back to a previous state. The most common example of this in the abstract world is file recovery. So we have some deleted file in our file system. There's basically some event that we know of that deleted this file. We basically want to reconstruct the state of the system or the state of this file to before the deletion occurred. And so we use our knowledge about the deletion process and the file deletion event to actually reconstruct to what it was before if we still have the available data to do this. We also have now abstraction and materialization. So abstractions basically, given the lower-level data, apply the transformations that the programs would have to define these abstract storage locations. So the common example of this is we import our disk image in that has just basically a whole bunch of sectors in it, and we abstract this into a file system. So we abstract this from a disk into partitions, our partitions into file systems, and analyze our files in various levels. And so we start with low-level things and move up to higher-level data storage locations. And this can occur for abstract events as well, and going in all these other various directions. And so there's some kind of dependence actually between these two, as we can have noticed here. That before we can define any of the other ones, we have to define the duration of the history, when this computer exists, what its times were. So this is kind of the main part in the whole dependency here. From there we can define what the storage capabilities were and the event capabilities were. And then from there we can actually start defining actual states and events. And similarly, after we have some states, we can then determine what programs existed, which allows us to determine which abstractions existed. So going to this picture here, this is probably too small for you guys to see on that screen. But down here is this notion of data abstraction, which is this analysis technique of taking the sectors from a disk, for example, and making a file system and identifying what files exist. For this process to occur, we actually have to determine, what file systems existed and what files existed and what abstraction types existed, which requires us to know the primitive state of the system, which requires the primitive, storage capabilities, and which requires an actual notion of the history duration of the system. So the benefit of this kind of dependency kind of graph is we can actually determine what assumptions are being made in practice when we go through this process, and a lot of these are actually skipped over in practice or can be skipped over in practice or just based on the assumption that they are true or that they are of various value. So if we examine the existing tools with these categories, we can basically break up our tools into two different categories. One is acquisition tools and the other is analysis tools. And the acquisition tools basically copy a state of a suspect's disk and make a copy so we can analyze it into a lab or some other location. And they basically, let me go back to the picture here, that we have original disks were being analyzed. At time t, we make a copy of this through a preservation program or preservation process. And at that point, we basically have two copies of the system from then on. And at time t prime here, if we want to actually analyze the system, we're going to use this to define a state of the system in the state's history. Now, ideally, we want to define this basically as being the state of the system at time t, which is when the copy was actually made. So we want to be able to say that even though this is 2 weeks later, we know the state of the system 2 weeks ago was this value. So to prove this, we actually have to show that nothing changed in this process. And this is what a lot of analysis tools will actually try and do. And the most common way of doing this is actually with MD5 sums or some other cryptographic hash value where you hash it over here at time t, and you compare the result at the current time to see whether it's changed or not, and we know whether we have an actual accurate value. And this is a reconstruction process that we discussed before in this primitive reconstruction, where we're basically starting with this state of our copy that we have and trying to reconstruct this state of the copy back to when the copy was actually made to verify that it hasn't changed over time. And the analysis tools basically, predominantly, allow us to define primitive states based on a copy where we can import some kind of sector-level copy of the system, define that in the system, and they basically make abstractions of files in various other forms. Chuck? Yeah, but the point is that the copy itself is then a file. Typically, it's a file from then on, and some other program in a system could have changed it, or it could have been maliciously modified to hide evidence. Essentially, from this time, let me show you here. That from this time on, at that time t prime, it's completely independent of the actual system. So they're depending on which precautions are taken to prevent changes to that. It may not actually be the same as the time t when it was actually made. Yeah. There's always cases of, the OJ claim of, oh, I didn't put that there, the police put it there to frame me, or these types of defenses that claim that, this was added there after it's acquired. Can you prove that this was the same as the actual system? So this gets into kind of reconstructing and showing that, at time t, this is the actual same as the system. So the analysis part, basically the current tools are basically very good at importing this low-level disk image. They can then abstract it. They know about various partition systems and file systems and application types like Word or HTML or PDF and email systems, and they can basically define all these higher and higher level abstractions on a system to allow you to view the data at these various levels. In doing so, they're not very good at identifying what's possible. So basically, they don't go through the formal analysis of saying, at this given time, what programs existed to make this abstraction possible. They basically assume that, or they basically show you the abstraction, whether the system supported it or not. So it's kind of the more efficient method of not having to analyze every program in a system and basically just showing you the data, whether it actually could have been viewed by the user or not. There's basic reconstruction support, again, for file recovery, as I mentioned before. And the reason that this is kind of the only one is that abstract events are very complicated and difficult to understand. And they can change with every version of every operating system and program. It's actually very hard to actually determine and enumerate all the various events that could occur to reconstruct states based on these things. So this actually occurs very minimally, or supported very minimally in programs. And so what's missing from most of the tools is basically a formal support for capabilities of what are the capabilities of the storage system and event system at both the primitive and abstract levels. The duration of the system, when did the system first exist to its current state? It's usually not crucial to an investigation beyond, did the system exist at that time frame, which is why it doesn't really exist. And again, said before, layers of abstraction, which is one of the impossible things that will never really be supported. So it's not really it's not really a major thing missing from the current tools. So the summary of this work is basically that we define a model to represent the computer's history, because the existing notions of the process models and various descriptions and approaches were kind of relatively ad hoc and organized based on a specific type of investigation or a specific investigator's experiences. In this general model, we can define categories based on these variables and show some kind of completeness with them. And we can show the categories with some kind of completeness to find all the variables and show that this actually can be used to define investigation with some kind of formality. We're a minute over, I guess. So sorry for the technical confusion there with these slides.
So where do you think, what's happening next in the next 5 years or so in digital forensics? You need to formalize techniques? Do you need to have new tools?
Well, this is, so the formality kind of stuff is kind of this debate in terms of, and I didn't get in this part of this talk either, but one of the motivations for us is actually the legal system kind of likes the formality of things and likes some kind of formal theory with it, basically for challenges. And it's kind of this unknown question in terms of what formality digital evidence will be held to in comparison to the other physical sciences. So there's what's called these Daubert guidelines, which are used to enter scientific evidence into court. And there's both sides that argue they don't apply or they do apply. And if they do apply, then it means they have to have formal testing and formal published procedures and kind of more of this formal process of defining how they fit into these categories. Bless you. But it's debate. But it's not clear whether they actually need to fit into that category. And it can be argued that digital systems are harder to apply this category or this rigorousness because they change so much. The possible events that can occur for each program change. For each release of the program, the attacker can come in and change them all, and it kind of remains to be seen with what rigor that the whole process can be held to because it's so dynamic and changing. So this kind of like paves one path that's used, but it's debatable to what degree it'll be held to, I guess.
Any other questions? Well, thank you.